In this example, we want to apply chain rule to find partial w by partial z. And given our function is function w is a function of r, s, v, and t, and the function relationship is w. We can write here this one. My w is a function of r, s, v, and t, and where r is a function of x, y, and z, and we having here s also a function of x, y, and z, and we having here v also function of x, y, z, and we having here t also function of we write here l, x, y, z. Now when we want to write the formula to find partial w by partial z, this means we differentiate respect to r, respect to s, respect to v, and respect to t, and then these derivatives we take respect to z, because we divide by partial z and multiply partial. So we get here partial w by partial r into partial r by partial z plus partial w by partial s into partial s by partial z plus partial w by partial v into partial v by partial z plus partial w by partial t into partial t by, but that's how we can write the formula. We can replace here z by any variable x or y, and we get partial w, partial x, and partial w by partial y. Only have to replace z with x or z with y. Now to want to find this value, we have the functions and we use this function partial w partial r. S is constant, v is constant, t is constant. Only r is changing. So get here 2r. So this will be equal to 2r, and into we having partial r partial z. Now x is constant, y is constant, z is changing, get here 2z. So this is equal to 2r into 2z plus partial w partial s. So r is constant, v is constant, t is constant, and partial, this will be 0, 0, and here I get v. So we get here is v into partial s by partial z. Partial z, we are having here our z is equal to xyz, and when we take derivative of z, that's equal to 1, we get x into y. So we get here xy. Then partial w by partial s. Again, r is constant, t is constant, v is constant, s is constant, v is changing. Partial w partial s will be equal, v will be equal to 0, 0, and here we get s. So we get here s into partial v by partial z. Now here in partial v, we have x to power e to power y, z is not appearing, so both are constant, will be 0. So I put here 0 plus partial z by partial w partial t. So r is constant, s is constant, v is constant, only t cube. So you get 3t squared. So you get here 3t squared into partial t by partial z, partial t by partial z. Z is appearing here, z squared is 2z, we get here 2tz. So this is my result. Again, because we have to write in the Cartesian coordinate system, so put the value of r, s, v, and t. We can write here partial w by partial z is equal to, we just make it small. We have here partial w by partial z is equal to partial 2 by partial r. What's my r? My r is equal to x squared plus y squared plus z squared. X squared plus y squared plus z squared. And then I have 2 into 2z is equal to 4z. I write in the beginning 4z. Then v into xyz. What's my v? My v is x e to power y. So put here v. I get the x squared y ey. X squared y ey. I simplify this one. This will give me 0. Then I have my t squared, but t squared will be equal to y squared z to power 4. Y squared z to power 4, y squared is not here anything, so we get here y squared is y squared, z to power 4 into z is z to power 5. So we have partial z by w partial z is equal to 4z x squared plus y squared plus z squared plus x squared y e to power y plus 6 y squared z to power 5. So this is my result. I want to put as a note the very important idea that sometimes we have the function like this one. I take as a note. We are having here the function w is a function of x, y, and z. And we are having here the function x is a function of t, a function y is a function of t, and a function z is also a function of t. If I take the tree diagram, then we are having a situation like this one. This is my w, this function of f, x, a function of y, and a function of z. Now here when we find x as a function of t, y is a function of t, and z is a function of t. Here w is a function of three variables. So we get here between x and w partial x, we're having partial w by partial y, we get here partial w partial z. But when we come to this one, x and t, x is a function of one variable, only t. Now this will give me dx by dt, this give me dy by dt, and this give me dz by dt. We want to write here the derivative of w, this is the function t. So I write here dw by dt because at the end is a function of one variable t. So when we write here, this will be partial w by partial x into, now we write dx by dt because x function of one variable. So also partial w by partial y into dy by dt, same concept, partial w by partial z into dz by dt. Whenever we have the functional and we have the discussion of the derivatives, when this function of more than one variable, two variables, three variables, we get the partial derivative. When function of one variable, then we take d by dt, not partial by partial, here partial by partial, only one variable, then we get d by dt. So that's the idea, just I want to take as a note. The next concept is implicit partial derivatives. It's very interesting. We have already studied that, for example, if we want to find the derivative d by dx of y square. Here function y is a function of x. Y is a function of x. Differentiate it. So we write it like this as dy by y square into dy by dx. So we differentiate, and here we get here is 2y dy by dx. Let's say we say the derivative we can define like this. For example, I having here the function of xy, and here we want to differentiate it. Then we have the product rule. We have here d by dx of x into y plus we have here x into dy by dx. Y is the function of x. This is y is the function. So here we get y plus x into dy by dx. For example, if I am having here the equation like x square plus xy plus y square is a function of x and y, and this is equal to 0. I want to find here dy by dx. Now in this case, I do the implicit differentiation. I take derivative of each of the term. I get here d by dx of x square plus d by dx of xy plus d by dx of y square is equal to 0. I take the derivatives. So x with x is 2x. So xy with y, as I have here, plus we are having the derivative, implicit differentiation, we say this one. We get here this is equal to plus x dy by dx. These are two terms. Then here we get here 2y dy by dx equal to 0. We take the terms we do with dy by dx together, and the other terms we take to other side. So we get here this has 3x and take to other side. I take x common. We take here dy by dx common, and I will get here dy by d. Here we are having not x, we are having here y. Here we get y plus x plus dx. So we get here y, and I take here dy by dx common, and inside I'll get here x plus 2y. I take these two terms on the other side, you get here minus 2x plus y. Now here, when I want to find the derivative, I just divide by the right hand side, the coefficient of dy by dx. So I'll get here dy by dx is equal to minus 2x plus y plus x plus 2y. So that's my result. Now I take an example. For example, I have the function fxy is equal to x square plus x sine y plus we have y cosine x, then we have plus x square y square, and then having plus y square is equal to 0. Want to find here dy by dx. Now I am interested to use the chain rule and the ideas I have generated to solve this problem with partial derivatives instead of this implicit differentiation that I have done before.